All right. So going to start the lecture today actually chatting about the lab. So the lab you just turned in. So a couple of closing comments about that before we get into the rest, I guess, of the lecture content. So so right now I'm also doing something slightly different with the way I'm sharing my screen, which hopefully is not noticeable to you, but is changes how things work on my end. So it can, again, in the chat, does everyone see a slide right now that says lecture post lab 2? Good, great, all right. All right, so I just wanted to talk briefly about the lab. So you just turned in this lab, you did a lot of hand simulation, and so I wanted to talk about some of the sort of similarities and differences in this setup, which was motivated by muffin baking, but beyond muffin baking, I think we'll see that there is a larger class of systems that are related to this type of thing. So for one, we look at these muffins, and what I'm hoping that you saw in this is kind of that when you're choosing entities, there's this new type of entity called a batch. And so you can either have individual muffins as entities because they're coming into the oven and leaving the oven, or you can have batches of muffins coming in where a group of muffins of maybe a random size comes in and then that group leaves. But then you can even actually have both at the same time. So you can have groups of muffins come in, get separated into individual muffins, sort of creating a whole bunch more entities. Then they can be processed separately and then rebatched later. So some of you had the opportunity, depending on your schedules, the schedules that were provided to you, the random schedules, that you might have had to create a partial batch. So in other words, you might have gotten to the point where there were only 3 spots left in the oven. You got a batch of 6 that arrived. So you had to break that into 2 batches, 3 that went in the oven and 3 that stayed out. So that's an example of this different type of entity where the entity is not kind of atomic. It can actually be broken up into smaller pieces and used as different types of entities, at least for a short period of time, possibly being grouped back together and possibly being left separated. And so this is a common feature of a lot of discrete event system simulations, the use of batches. And so this was meant to kind of introduce you to this idea that not only can you have entities, but you can have batches of entities as a type of super entity and so on. So that's kind of what we were trying to show off here. So that was one of the things we tried to feature. We also hopefully noticed that you had deterministic arrival times. So you knew that every time period, you're going to get a batch of muffins that arrive. But the number of muffins in that batch was the thing that was random. So we didn't randomize time, we randomized quantity. And this is common in inventory management problems. For example, you know that you're going to open the store every day, but you don't know how much demand you're going to get that day. How often are people going to order the product that day, or how many are they going to buy out of your inventory? And then similarly, you can have an inventory management person come and check your inventory every day. And so that person comes every day, but the amount of inventory depleted is going to vary every day. And so the amount of inventory that person may have to order, which then will have a lead time, so it may take a couple of days to come back to the inventory, that is going to be randomized. And so sometimes the random thing, the stochastic thing that we're modeling, is not a time thing, but it's like a space thing, a quantity thing, the number of. And so inventory management is normally where you as industrial engineers and operations researchers will see this. A few of you might go off and become quants somewhere, and actually go off and maybe do financial work. And you see the same type of stochastic simulation in this example that I've put here on the slide, where sometimes you have to build stochastic simulations of financial data, of say stock market data. So if you think about that, every day you look at a stock, that stock might go up or down. You know that you're going to look at it every day, but the amount that it goes up or down is going to be random. And so when we're modeling muffins, we might have some physical process that helps us understand how many muffins are going to come up every day. But when you're modeling stock market data, it's a lot harder to sort of figure out, well, how am I going to make a good guess as to whether the stock's going to go up tomorrow, down tomorrow, and so on. And so these portfolio management models that people use, have to make statistical assertions about what they would expect about these trajectories that you would want to simulate coming out of that. So you might say, well, we know that on average, so this is a martingale process. This is the term that you don't need to know for this class, but if you go on further in stochastic modeling, you'll see this term a lot. So a martingale process is one where the expected value of the next point in your sequence, and so we'll call it the expected value of tomorrow's price, is equal to today's price. So this makes sense for stock market data because it might be that whatever the price is today, you want tomorrow is going to be a distribution of prices. And you just want that the average of that distribution prices equals today's price. And then it's going to change. And then the next iteration, the new average will be tomorrow's price for the day after tomorrow, and so on and so forth. And so you can build stochastic models that have this constraint. And then you just have to figure out how to add the variation around that constraint. And so this is one common way that people do that. And then what you would do with those things, if somebody wants to experiment with a portfolio management strategy, they want to say, well, I want to have some robot that I build that automatically buys and sells whenever I see certain signals from the market. You want to test the efficiency of that robot before deploying it on the real stock market. And you might not like the real stock market historical data because it may not have all of the terrible things that could possibly happen. And so what you do is you can generate a stochastic simulation of stock market data. And as long as that's statistically similar to real world data, then it becomes kind of a stress test for the algorithm you built to buy and sell shares. And so that is sort of, somehow related to this kind of inventory management problem where you're like, I don't know how many muffins arrived today, but based on certain things that happen, I might run my oven differently. And then if I just kind of stress test my oven, baking algorithm with this stochastic simulation, then I can see, is it ever going to be possible for me to have a huge pileup of muffins that may be to the point where some of them, go stale or something like that. So those are kind of the motivation for these types of problems that we're looking into here. So before I look at some of the data that you guys came out of that lab and some of the questions that were asked in that lab, are there any questions that you have about the motivations for this muffin baking lab or about anything I just mentioned about inventory management problems? Just give a little bit here. Okay. All right, well, in that case, let's just, for kicks, do an early attendance exercise. And so in this attendance exercise, I'll put the URL in the chat if that's easier. Then the question I have for you is, I just mentioned that there's this term martingale. And it relates to, we can just say for a stock market, how tomorrow's price relates to today's price. So in your best kind of, description, it could be a mathematical one, that's fine. Can you tell me, what is a rough description of a martingale? Or what property, I'll say, or what property does a martingale have? So that's the first attendance question for today. Let me put that down. And again, that's not a term that you're going to need for 475. But if you go into more advanced simulation courses or just stochastic modeling courses, you'll see that term martingale, sub-martingale, super martingale, and so on. These are common terms for modeling these types of sequences.
Hey, Professor.
Yes.
Do you want us to submit this after we fill out this first question, or basically?
No, don't hit submit, just leave it in a tab,
Okay.
Open in the background, and then the next attendance question will be question 2, and if there's another one, question 3, and then you'll hit submit at the end of class.
Okay, perfect, thank you.
And of course, if you're watching this asynchronously, you've got 24 hours after I post this video, and you can submit these as well. Okay. All right, so let's move on here. All right, so basically I gave all of you randomly, and I'll get to these questions. I haven't answered these questions yet on the labs. And so just sort of straight into sort of the lab data, sort of what we should take from the labs. So I gave everybody 10, well, not everybody, I gave randomly, by randomizing by the last digit of your ASU ID, I effectively gave each one of you a different schedule of muffins. So if your ID ended in 0, you got muffins, you all got muffins that arrived over a 30-day period, but some of you got 5 muffins on the first day, some of you got 10 muffins on the first day. And by 10 muffins, you could also think of these as 10 muffin orders. Like you got, 10, somebody came in the door and they asked for 10 muffins. And so you had to figure out how to bake these 10 muffins. So, so then after each one of you ran through these schedules, you ran the exact same schedule through the greedy policy, and then you ran the exact same schedule through the nearly full policy. So it was in testing 2 hypothetical worlds, one world where you used a greedy policy in your bakery, and the other one where you used a nearly full policy in your bakery. But in both worlds, you had the same customers coming in asking for muffins the same way on all of the days. And so you came out, and some of you might have gotten a greedy policy with an average time in the system of, I don't know, 3.9 or something like that. It might differ for you because I just picked one of these. And then some of you might have gotten an average nearly full policy of 4.15. So here it looks like the greedy policy is better than the nearly full because those muffins don't wait as long. They don't spend as much time in the system. So one of the questions I asked then is, can we use this data, these data, is this useful? Can we actually make a good inference about this? And does anybody have an answer to that? And I guess the hint is that the answer is supposed to be no, that this somehow isn't enough for us to actually make a useful inference. But why? Does anybody have a good answer for that? And it might, and what the output results I'm seeing here are just from a single schedule. So let's call this, I don't know whose ID this was, but let's say this is an ID ending in group 0, or ending in number 0. I'm seeing a couple of interesting answers here. So I'm seeing sample size is too small of sample size. And then I see because we should use a hypothesis test. And so those seem like there's sort of 2 related, but kind of responses on different levels. A single schedule isn't enough to reflect typical performance. I see that. I see need at least 10 of each simulation model to be reliable, because it depends highly on initial conditions. So that's, so I guess it depends on what we mean by initial conditions. For me, for this problem, the initial conditions are the same in all of them, because to me, the initial conditions is it's an empty oven and there's no ovens waiting, or no muffins waiting. So that's what I mean by initial conditions. They're the state of the system, and the schedule coming in, I don't view as an initial condition. I view that as an input. But I understand if you're thinking of the inputs as kind of initial conditions, then yeah, I would say that that's important too. I see, would it be that the muffin batch schedule wouldn't necessarily be random in real life? Would it follow a more uniform distribution? That's an interesting question. So that's something that wasn't quite getting at here, but I think that's a very valid point, is that maybe in real life, you would get exactly 5 orders per day, exactly. And we randomize them, so sometimes you get 5, sometimes you get 3, and maybe that was a bad input model. So I mentioned before, kind of like when I showed the fashion model faces going in and the fashion models with the fashion coming out on the output, that if you pick kind of bad fashion models, then even if you get good looking results, you're actually going to make a bad inference. Like you're going to think that dress would look great, but then when you actually buy the dress, then you find out that, well, it looked great on that person, but there's something about that person that isn't quite the same with me, and it doesn't quite work with me as well. And similarly with this muffin schedule, you might get results that are more a function of the muffins that you put into the system than the system itself. So that is certainly valid here. But here, let's just, even if we say that these muffin schedules were realistic, let's say these were from real data. So I took, like, each one from maybe, over 10 years, I went back in January and I took 30 days in January over all 10 years. You can say, well, maybe things change over the 10 years or whatever, but let's just imagine that these are realistic numbers for these muffins. Then I think these questions about, then these comments about hypothesis test and number of samples are interesting here. See, to me, I would view these outputs as a single sample. I took a sample, it happened to took 2 measurements of that sample, and I took a greedy measurement and nearly full measurement. What I mean by that is for this single muffin schedule, I measured it 2 ways. I said, if I were to shove this muffin schedule through a greedy system, I would get this performance. If I were then shove this muffin schedule through a nearly full, I would get this other number. And so for this particular schedule, it just so happens that greedy is better than nearly full. But the real question is how generalizable is this schedule? And if my claim is that this is one of the 10 different schedules that you could get, then what we need is we need more schedules. Because otherwise, there's 2 problems here, is that for one, without having more schedules, as far as I know, this could just be bad luck. I just picked a bad muffin schedule going into it. I picked a muffin schedule that happened to make the greedy policy look really good. This is just like picking a fashion model that makes a particular jacket look really good because it only looks good on that fashion model. That might be the case here. And so I need multiple models to put on that jacket to tell that the jacket is actually good on multiple different body types. Here, I need multiple muffin schedules to push through these ovens. And if all of them show that the greedy muffin schedule is better, then I can say that the greedy one is better. That's the first problem. The second problem is a problem of practical significance. And that's if I look at the difference between these, I don't know what actually makes a difference in the whole cost-benefit analysis of it all. So I might be able to show statistically that the nearly full schedule is slower than the greedy schedule by, I don't know, 5 seconds, 5 seconds per muffin. Well, then we have to ask ourselves, let's say that whatever I would need to do to reorganize my bakery to use the greedy schedule in real life would cost a significant amount of money for that reorganization. Is that cost of that reorganization worth the 5 seconds per muffin? So that's practical significance. So there's statistical significance, which is basically answering the question of, are these results purely due to chance? And then there's practical significance, so that I've demonstrated that I have a significant effect, a statistically significant effect. Is this effect actually large enough to be useful in the real world? So if I drill down into that, I can put all of your 10 schedules together. So this is all of your results. And so if you were to ask your neighbor what results they got in the lab, which you could do now because you've turned in the lab, then one of your neighbors would have gotten one of these numbers if they did the simulation right. And the same thing for this. And so here I now see that there is a variance in all of the greedy ones. So I give you 10 different greedy schedules, and some greedy schedules are really fast and some greedy schedules are slower. For those same 10 muffin schedules, the exact same, you push them through the nearly full policy and you get this variance here. And you can see that some nearly full are really slow and some nearly full are pretty fast. If you were to compare this point up here and this point down here, it would, and that were all you were to compare, then you would maybe decide that maybe the nearly full is faster. But that would again just be you reflecting something by chance. When I look at this cloud, to me, it looks like the greedy policies are always a little lower than the nearly full policies. To me, when I look at this cloud of points, then I get the hint that the greedy policy is the generally faster policy. You might be able to come up with one muffin schedule where nearly full will win, but most of the time, the greedy policy will win. So for 99 or 95 or whatever percent of the schedules that you give it, greedy is going to be better. That might be the case. But then there was that comment in the chat, we need a hypothesis test. Really, in order for us to make any sense of this, we can't just look at the clouds. Then we do need a statistical test to test these two means apart. And so you guys have learned to test means, to say, You know, I don't know what the population mean is for the greedy strategy. I don't know what the population mean is for the nearly full strategy, but I just took a bunch of estimates here and another bunch of estimates here. Based on my estimates, can I make an inference? What is the chance that the population mean for the greedy strategy is actually lower than the population mean for the nearly full strategy? And that's effectively what you get with a t-test. And so a t-test tests means. We have two populations, a greedy population and nearly full population. And we have data that's been taken from those subpopulations of muffins. So you can think of this as muffins in the greedy and muffins in the full. And so we use a t-test here. I heard a question or an unmute. Was there a question? It's funny, the random unmute is like the stretching in class. It's like, oh, did you have a question? No, I'm sorry. My back hurt. Okay, I'm sorry. So, all right. So, that's getting where we need to go. But we have to ask ourselves, the t-test that you learned in whatever, 380, 385, would it be directly applicable to the 10 data points on the left and the 10 data points on the right? Could we use a traditional two-sample t-test? And then we say one of the assumptions of a t-test is that all of the data on the left were drawn independently of all of the data on the right. They were independent random samples from populations. But the problem here is that these weren't drawn independently. If you remember, there are 10 muffin schedules. And for each one of those, they generated 2 points, a point over on the right and a point over on the left. So I wasn't like, these are just a random set of 10 muffin schedules, and then I threw all those muffin schedules away, and then another random set of 10, and then did those 10 muffin schedules with the nearly full. Here, I've taken each muffin schedule, and I have put it in to both ovens simultaneously. And so that means that I can't use a traditional t-test on these data. And this is actually something we do on purpose because it actually makes it easier to compare across schedules, because we can now pair up and we can say, well, I said, you know, this point up here, this might actually pair with this point up here. And if those two are paired together, then that indicates that this is just generally a tough schedule. For this schedule, any policy is going to give us a slower time per muffin. And so by pairing these things together, then it helps us better understand sources of variance. Because I could just have variance in my muffin schedules, but, and so I want to be able to sort of tease out how much variance is due to my choice of policy. So greedy, so you can see here that already we get the feeling that some of the variance across the blue and the red points is just due to the fact that one's blue and one's red. So the greedy policy has some effect. It generates variance. If you put things in the greedy policy, they tend to be a little lower. But to figure out exactly how much lower, we need to know how much of the spread in the red and how much of the spread in the blue is kind of common to both. And that's where we use pairing approaches. And so that's something that we're going to use later on after the midterm. We're going to talk about using common random numbers. And that is this common random numbers is a way for us to have the computer generate muffin schedules for multiple policies simultaneously, and then run multiple different types of sims, all with the same inputs. And by doing that, then it helps us better compare across the simulation types, because we know that they all have the same inputs. We have to make sure that they all get many different types of inputs, but for every input we put in, we run that same input across every single type of simulation. Here's a bank teller, or here's a bank with 1 teller. Here's a bank with 5 tellers. Here's a bank that's just totally automated. Well, we want to run the same customers to all 3 banks and compare. And by using the same customers in all 3, then the natural variance in the customers can kind of be factored out, so that whatever's left over is truly the difference in the policies themselves. And so that is something that we'll talk a lot about later. But I just want to give you a hint of what's coming up. So for now, the way we can depict that is every single point from the greedy policy we can pair it with the point from the nearly full policy that had the same muffin schedule. And if we look at these, then now we can see that almost all of these lines have got an upward slope. You know, I don't know if my camera might be mirrored, but hopefully you can see that they all move up an upward slope. Okay, so I see a question in the chat. This is a private question that said, could you please repeat why the samples were not independent? Yeah, sure. What I mean by that is that the samples, there are 10 samples on the left and there are 10 samples on the right. Now these could have been generated by creating 10 muffin schedules on the left and then 10 totally different muffin schedules on the right. So, but when I had you hand simulate these, you used the same muffin schedule for both your greedy and your nearly full. And so the data going into both muffin schedules simultaneously were the same. So they would be independent if we randomly redrew 10 new muffin schedules for the different treatment type for nearly full. But because we used only 10 muffin schedules and generated 20 data points, we effectively, each muffin schedule generated 2 data points. Each muffin schedule generated a greedy and generated a nearly full. And so those 2 data points, greedy, nearly full, are not independent because they were generated with the same background information. They were both generated with those muffin schedules. Does that help to the person who asked the question? Okay, good. All right, and so the way I've depicted things here is typically one way that we depict that we have created a so-called paired design. So a lot of this class is about statistical design, and this is a statistical blocking technique. And so we have created blocks of outputs so that these outputs go together. And so this red point here on the left goes with this blue point on the right because they both had the same input going into them. And so that then, we look at all these lines, they all have basically the same slope, and that gives us the impression that there really is an effect of the nearly full policy. The nearly full policy is slower. To make that even clearer, then what we can do is we can say across our 10 schedules, which I've now plotted on the horizontal axis, I can plot the greedy policy for that schedule in blue, and the nearly full is this red asterisk. And so they show up on top of each other, and I put a little line in between them to make it clear that they go together. And by plotting them this way, then I can see that the red points are always on top and the blue points are always on the bottom. So it further amplifies this pattern that the greedy policy is faster. So, we've got this here. And so what I can further do is for each one of these pairs, I can subtract. I can measure the length of this line. And when I measure the length of the line for this pair, then what I find, these are all of the differences. These are all of the lengths of those lines. And I find out that this difference that I took, greedy minus nearly full. So if I go back to this line, the greedy is the blue, which is down here. If I subtract the nearly full, then all of these greedy minus nearly fulls give me negative numbers. So if I put a 0 here, this shows that they're all showing up negative. And this is something that I now can do a t-test on. So I can ask, is this cloud of points statistically different from an average of 0? And that's the so-called paired difference t-test. And so that's what we're doing here, this paired difference t-test. And we find a p-value that is far less than 0.05, which tells me that there is a statistically significant difference from 0, which means that the greedy policy's mean is different than the nearly full policy's mean. And so I was able to do this paired difference because I created these statistical blocks. And these statistical blocks ended up showing off more of the differences between these two policies, greedy and nearly full. So that's what I mean by a paired difference t-test. We're pairing things that have a similar history so that we can factor out the effect of the history itself and compare those two. And then we can now do a proper statistical test that this one, we actually can apply a t-test to this data, these data, but not to the two groups because those two groups weren't independent. So any questions about that? So that's why you can't just So why you can't, I think the first question was like, why can't you use a single data point? Well, you need more data points because it might have just gotten lucky. And then I think I also asked, why can't you use a standard t-test? Well, I can't use a standard t-test because the two populations, greedy and nearly full, the individuals we sampled were not sampled independently, that they're related to each other. And because of that relationship, I needed to pair them and then come up with a metric that measured for the same individual, what's the difference of these policies. Then I could take all those differences and compare those differences to 0. And to that, I can apply a normal t-test. And this is all stuff that we'll drill down more deeply after the midterm. But I just want to give you a hint of where we're going with a simulation like this with these random data. All right, any questions about that?
I was wondering with, so one of the questions was how to compare to other people. So like if we were to compare to everyone else in the class and their values, how would we compare? And would one way also be like just to like visually represent it? Could you do a box plot for the differences between the policies? So you would sum all the policies, all the nearly full policies and all of the greedy policies, and then make a box plot each for those, and then compare the two box plots. Would that be like a visual way to represent it?
Yeah, the visual, so that is effectively what, so basically what you're saying is this image here, you could replace this with box plots, and you could. And that would be a visual way to represent these data and the spread in these data. I usually only resort to box plots if I have a high number of data, because if you think about all of the points on a box plot, you've got like, if you consider like the whiskers and the outliers and all that, then I forget how many points you end up getting, but let's say it's, 8 points or something like that. If you have 10 data points, then the 8 points of your box plot almost are your data. But yes, if you had a large amount of data, then you probably would not plot the raw data like I did here. You probably would use like a box plot. Now, the downside of just using a box plot is that they show visually where the differences are, but they don't give us an idea of statistical significance. Now, I'm going to teach you some tricks so that you can rigorously infer whether two populations are statistically different just by looking at effectively their box plots. But those tricks only work if you had two independent groups. And so they also will require that the greedy policy used a different set of inputs than the full policy. And so, so that's something that, visually you can kind of get an idea that something's there, but in order to rigorously know if the results that you got aren't just by chance, we have to use these hypothesis tests. And so that means that we are going to have to calculate a p-value eventually. But if things are far enough apart, there are ways to use certain visualizations and guess what the p-value is going to be pretty correctly without actually calculating a p-value. So, but all I was really looking for in that lab question was you to say, well, because we all had different schedules, we could all pool our data together and then look at, basically do this. We could all do this. I could get together with my classmates and we would eventually have enough data on these two policies to be able to make an inference that would be unlikely to be just due to chance. And so your single observation for this single muffin schedule wasn't enough. But if you talk to all of your classmates, then you'd have 10 independent muffin schedules. And you could then see across these 10 independent schedules, do we see a trend? And if you saw that trend, it'd be much more believable than your single data point. Any other questions? So these are the things that we have to deal with stochastic simulation, is that our outputs are going to be variable. So we're going to have to run multiple simulations, even though we don't do anything, we just have the computer generate new random numbers. And then we're going to have to use statistics to compare across, because sometimes the computer is going to give us just purely good luck inputs that make the outputs look good. All right, only other things that I wanted to hint on here, the last couple slides, is that other complications that we will talk about later in the semester is that I think are very realistic as you think about real systems is choosing the output. So there were outputs that we could have said, well, we had time in system, average time in system, there was average oven utilization, and there was maximum queue length. These are three different outputs that we can take from each simulation. And so then the question is, which one do you use? Some of them, like this average utilization up here, shows a statistical difference, a statistically significant statistical difference, but the other two do not. So if you just happen to choose one of the other two, you might have said that, well, you know, these two Muffin schedules are identical. So then we run into this, we say, well, maybe you just got lucky by choosing a metric that happened to be different. Because if you think, what is a p-value? A p-value says 5% of the time we're going to detect a difference that isn't actually there. Well, so if you pick a bunch of tests and each one of them has a 5% chance of incorrectly detecting a difference, the more tests you pick, eventually one of those tests is going to detect a difference. So we have to figure out, how do we deal with this fact that if we measure multiple outputs, how do we somehow make use of all of the information about all of the outputs without so-called fishing for a difference? And towards the end of the class, after the midterm, we will talk about how to properly weight your p-values so that you actually can take multiple differences. So you can properly say, okay, well, it's because I can measure three things, I can actually make use of all those three things and be able to tell if I've really detected a difference across those three things, even if only one of them tested alone would detect a difference. So that's something, again, something looking forward. And this is the so-called multiple comparisons problem that you'll see in units I and J. And we'll talk about things like the multivariate ANOVA, multivariate regression, Bonferroni correction. These are all things coming up after the midterm. But this is the kind of what you should be thinking about as we get into them is, how do I choose an output? And what do I do when one of my outputs shows a difference and the other one doesn't? There are tools for that, and we will get to those tools. The other thing that I just want to hint at is that you could have rethought this greedy versus nearly full policy as a policy of oven threshold. So do I immediately put things in? That's kind of the greedy policy. And then the nearly full policy is when the oven threshold was just set to 20. So if I've got 20 or more waiting, then I put them in. Well, I could have thought of this oven threshold as a more smooth variable that I could set from any value, from 1 all the way up to 30. And then I could study simulations for each one of these things. And instead of asking, does the greedy policy do better than the nearly full? I could ask a more interesting question, like what is the effect of oven threshold on performance? And so if with all of these data where your nearly full is here at 20 and your greedy is here, and then there's a bunch of other policies here, then I start seeing some patterns arising here. And so those patterns are why we have linear models, is that linear models help us to better understand those patterns so that we can see that, that in general, as you increase your oven threshold, you are going to increase the average time in the system. Now we can do much more sophisticated modeling to try to point out here that, well, it looks like things are pretty flat and then they start rising. So it's almost like there's a critical oven threshold, that if I'm below that, the oven threshold doesn't really matter. But then above that, I get this linear increase. And so these are the kind of more sophisticated statistical questions you can ask about these data. And so sometimes you need to ask yourself, did I really need to create two groups, or am I really just testing two values of a larger variable? And really what I'm interested in is, how does that variable make an impact? And that's maybe the better question to ask. And so a lot of people have actually moved away from hypothesis testing that's kind of A versus B and towards just pure linear modeling for everything, because linear modeling has not only can give you everything hypothesis testing does, but it also can give you the ability to detect gradations in effects as well. And so that's stuff that we'll talk a little bit more about later. All right, and so there's some extra slides in there that I'm not going to go over, but they're online that you're happy to take a look at if you want to see some other additional insights. But that's just a preview of what's coming up. All right, any other questions about the lab? We've got a short lecture otherwise.
Hello, Professor?
Yeah, uh-huh.
So for the bonus question, about comparing maximums. I noticed on your previous slide, you're just comparing how that nearly full threshold changes the maximum Q, but why would a t-test be inappropriate if we just fix maximum Q to 20 like we did in the lab and then just compare the maximum between multiple different schedules? The bonus
Right.
was like, why is it inappropriate to use a t-test?
Gotcha. Excellent question. So if you think about all of the assumptions for a t-test, one of them is that you have to have independent samples. But the other one is that it's got to be a continuous variable. Now, you can get away with if you have a large enough range. So if your discrete variable goes from like 1 to 1,000 and assumes nearly every position along that, then you probably can get away with a t-test. But in general, t-test is only used for continuous variables. And so the trick for that bonus question was that it was asking about a Q length, and lengths are counts. And so the Q length may have been, like, let's say the Q lengths are just either 4, 5, or 6, and that's the only values that they ever took on. Well, then that 4, 5, or 6, because there's no chance of there being 4.5, there's no chance of it being 3.2. I mean, a t-test effectively requires your data to be normally distributed, that the population comes from a normal distribution. A t-test is built upon the idea that I'm testing two means from populations that otherwise have a normal distribution. And the simplest t-test assumes they even have the same variance. And so if I'm now testing lengths, Q lengths, a length does not come from a normal distribution because it can only assume whole numbers, and it can only assume a small number of them. There's no long tails that could have possibly assumed. So if you look closely, when I did something that is equivalent to a t-test, but for these lengths, I didn't reference a paired difference t-test. I used this thing, SR, which is a signed rank test. And so there are analogs of t-tests that can be used when your data are not normally distributed. And we will talk about those a little bit later on. So all that I wanted to get in the bonus is if you go back to remember that a t-test requires you to make the assumption that your data come from a normal distribution. And Q lengths, which are discrete variables, are not going to come from a continuous normal distribution. And so we technically cannot apply a t-test unless those Q lengths are scattered everywhere and have a huge range, so that we, if we were to sort of plot a histogram of them, it would fall on a pretty good bell curve. But so things like waiting time, we can often get away with because waiting time is smooth, at least. Now, the problem with waiting time is it's often at a heavy tail, and unless your waiting times are very, very large, it doesn't look very normal as well. But for discrete random variables, those are like red flags. Like if I see a discrete random variable, I might in my heart want to use a t-test, but I need to go out and find a so-called non-parametric t-test or a non-parametric test of means. And we'll talk about those non-parametric tests. So that's what I'm getting at there. Does that make sense?
So the signed rank would be an appropriate test to run on this?
Right. So we're going to talk about something called a Mann-Whitney U-test. And a U-test is meant to be a t-test for non-parametric. The paired difference version of a U-test is a so-called signed rank test. And so that would be kind of the appropriate thing. So if you were to look up signed rank or U-test or non-parametric paired difference t-test, then you would find things that would bring you to this material. But I will talk about this material probably, I think, after the midterm. I'll give you kind of a decision tree of how you should choose these tests. Most of the things we do in this class, it's going to be fine to use a t-test for. The most exotic thing you'll have to do is maybe turn it into a paired difference t-test. But in the real world, your data are often not going to be normally distributed, which either means you're going to have to run them through a transform to make them normally distributed, or you're going to have to find one of these non-parametric tests, which are kind of like less powerful versions of the t-tests that you've learned in school so far.
One last thing. So I was going through the chapter, the chapter of discrete distributions in our 380 textbook, and I was trying to think of what would be a good distribution to describe this maximum Q, and would it just be the Poisson distribution or some variant of that? Or it just seems like, I don't know, you're applying some kind of schedule to it, and then you've got a Q, and that Q seems to be, I couldn't really think about it in my head very well. Or is it just going to be some other random discrete distribution?
Well, so you mean for the inputs coming in, like how many
No, not
numbers
for
of
the input
muffins?
coming in, but for the maximum Q.
For
Because one of the things I wrote for the answer was that it doesn't come from a normal distribution, but then that made me think, what distribution does it come from?
Right. Well, there may not be a so that's kind of the beauty of the stochastic modeling is you start with on the inputs, you start with distributions you might recognize, and sometimes you won't recognize them, and we'll talk about later on, actually even before the midterm, how you start to build input models, so probabilistic distributions that don't come out of the book, that are bimodal, for example, or multimodal, you know, have tremendous skew and all these things that don't fit any particular one. We'll talk about how to deal with that. Now, coming out, they very often are even worse. So coming in, they'll look like tidy normal distributions, exponential distributions, et cetera. But as they get reshaped by your process, then they will take on a totally different form. Now, fortunately, coming out on the output side, we don't actually usually have to fit them. We normally need to find statistics that are appropriate for them, but we don't need to come up with a fit for them unless we're going to somehow use our simulation as an input model for some other simulation. But that does happen, but that's kind of a much more advanced setting. So you may not be able to come up with like, okay, this makes sense to be a Poisson distribution. A Poisson distribution makes sense for when you have exponential inter-arrival times all arriving within a finite period. You could say, I'm going to count all those things up, and that will be a Poisson distribution. That will be that number of counts. But coming out of this thing, then these things, you know, because of the muffin, the oven takes 3 minutes. And so even though they came in kind of spaced out randomly, they're going to go into the muffin and they're going to come out uniformly. You know, every 3 minutes, you're going to get a new chunk of muffins coming out. And so the outputs of our systems are often not going to meet the nice, tidy assumptions that go in to the beautiful probabilistic models that we have on the inputs, if that sort of makes sense. And we'll talk about that more as we go on. I also saw, there's a question, another private question. So there's a question about would it be appropriate to say that a t-test would not be, is used to compare means but not maximum quantities. So this is a kind of a funny thing here, is that you're still in this maximum Q length thing, you're actually still comparing means across populations, but the thing that you're comparing is the maximum. So I come out of every simulation and I calculate a maximum. For all of the muffins that went through this simulation, there was a maximum waiting time. Bam, maximum waiting time. That mean is then, okay, of the population of simulation runs, what is the average maximum? And so a t-test is comparing averages across simulation runs. But within the simulation run, the performance metric is taking a maximum across muffins. So, so that, I guess I wouldn't, so the question was, would you still get credit if we said a t-test would be inappropriate here because it's a maximum and a t-test address means? That's not quite right, because we're looking for we're testing the mean maximum. And so it still is testing means here. But it just happens to be that the performance metric happens to be a maximum metric across muffins. So you got many muffins within a sim, but then many sims. And we're trying to make an inference about the average across sims, even though the metric is about the maximum within a sim. All right, any other questions about the lab? Okay. All right. So today was almost meant to be kind of a bonus lecture, that gives us time to talk about the lab, and then also talk about, if we have a chance, you'll be able to see for the homework that's due, I think, today, we'll walk through the rough idea of how to build the spreadsheet that solves the bonus problem on that homework. Today's class here, homework B1, again, if I remember my Canvas correctly, I think I have a due tonight. There's also a Canvas activity, one of those interactive activities due before the next lecture, before lecture C1. Just as reminders, the Rockwell Arena competition's out there for those of you who are interested in using this for your final project. Then you should probably be pulling together teammates and then consider submitting, because I think registration is due at the end of September. If you're looking for access to Arena, you can find them on the BYNG 214 computers or from remote. And so anybody on any platform can go through the VPN and connect remotely to the computers there to get access to Arena, even if you can't install it on your local machine. Also, if you're thinking about that competition, FlexSim is another competition. I think they also have a deadline coming up, I think at the end of September. Simio is another one I don't know as much about, but there's, I think I've got a link here in the PDF that you can get to. If you click on the PDF that's on Canvas, you can see the Simio competition. So I'm willing, just let me know if you're interested in those instead of the Arena competition, and we can talk about that to do those instead. And if you find any other discrete event system simulation competition, we can also talk about that. All right, so any questions about things that are due, things that are coming up? Okay. All right. Okay, so your homework, you're going to be building something that looks just like this. Hopefully by now you've had a lot of practice between the lab and working on the homework and getting it that way. So I'm not going to go through and step by step the way we did last time. I do have all of the steps we're producing on the slides. So I'm going to kind of move through them, but I want to just point out a couple of things along the way, just in case you didn't see them. So this table, which is what's required for you to generate on the homework, plus an F column for the cumulative statistic, is just a tabular version of what I've shown on the timeline here, all of the events that occur in this single channel queue. And so you can go through these things, and what we see is that between every arrival that shows up on this timeline are exactly the interarrival durations. So in theory, you actually could predict when every arrival is going to happen, because you don't have to, arrivals don't wait for the next one. Like once you get one arrival, you can schedule the next arrival. So in theory, you could actually go through and schedule all of your arrivals all at once. You should not do that. That's not the way the computers does it. This would get you into trouble in more complicated systems later on. But in theory, you could schedule all of your arrivals up front. And you would see that the difference between all the arrivals would match exactly the difference in the inter-arrival durations. And we refer to those as activities, because those durations are known ahead of time. So I'm able to predict what's going to happen in those each interarrival duration without running the simulation. That's what makes them an activity. Now, there are another set of activities. Those are the service durations. Those come from the second row in your homework. And those service durations, I also know ahead of time. So I don't know when the service is going to start. But once it starts, I can then figure out statistically how long it's going to take. And so because I know those ahead of time, those are activities. Now there's a gap between these activities starting. That's the thing that I don't know until I run the simulation. And so those gaps, and so there's a gap here, arrival of customer 3, when does customer 3's service start? Well, customer 3's service start happens right here. So there's a delay that customer 3 has to wait. All of these delays, so these are all the delays from the arrival of a customer. So this is a delay that's just idle time, how long the server is waiting for the next customer. And the rest of these delays are how long each customer waits before their service starts. And those delays, I don't know ahead of time. I have to run the simulation to figure out those delays. And that's what makes them delays and not activities. I don't know the statistical distribution of those ahead of time. Afterwards, I might be able to fit a statistical distribution to them just for fun, just to summarize the data. But the whole reason I run the sim is that I have no guess at what those are ahead of time. I have to use the sim to generate those for me. And that relates to one of the questions we had during the lab questions. So sometimes we're going to use the term unconditional wait to represent an activity. So it is a waiting period which is not conditioned on, I'll say, the input. Here it's going to say to not depend on any conditions of the system. And I'm just going to try to make that a little more precise. It does not depend upon the history of the system. It does not depend on the input and the history of the system. This is also sometimes, so an activity is always going to have bookends. It's going to have an event on both ends of it. So the completion of an activity is an event and the beginning of an activity is an event. Everything in between them is the actual activity. So the completion of an activity is sometimes going to be called a primary event. And so whenever we start an activity, that means that we're going to have to schedule an event into the event calendar, which will be the completion of the event. So you can think of this event as sweeping up after the activity. So we know that service just started, so we need to know when the service ended. The only way the simulation is going to know when to end the service is at the instant the service starts, we schedule when the service is going to end. How long is the service going to take? Well, that's going to require us going into a statistical distribution of how long these services take, drawing randomly, and then placing that endpoint at that random duration out in the future. And then that will then mark the end of that. And then we can, eventually our sim will get there, and then we can do more scheduling once we get there. On the flip side of that is the delay, which we're going to sometimes call a conditional wait. I say here it's conditioned on system state. I can make that maybe a little more precise to say it's conditioned on the history of the system and the input. And so we don't know what the delays are until we run the simulation. Its duration depends upon the appropriate conditions. It's caused by interactions with activities. And so activities may not line up properly and they have to wait on each other. And so in order for one activity to start, it has to wait for another activity to end. And so that waiting period, it ends up being a delay. And so it's the mismatch, the misalignment of activities that generates these delays. And so, these delays are not going to generate any events, like our activities required us to schedule, but the events scheduled by other activities will kill delays. And so we scheduled that an activity, say a service duration is going to end in the future. When that service duration ends, someone else's service can begin. And when their service begins, their delay, the amount of time they were waiting for service, finally dies. So they finally can begin the real time, the real value added time of actually being in service. And so events terminate delays by changing system state. By freeing up resources, events can terminate delays. Some people, like your arena, will refer to two different types of time: value added time and kind of like all the other time. Value added time is time in an activity, whereas all the other time is just wait time. So, so that's, you know, what do we mean by value added time? I'm actually waiting, getting the thing done that I gained, you know, I'm at the bank teller. They're actually doing the work. The non-value added time is the time where I'm waiting for the bank teller. So that's another sort of, you know, some terminology. All right. So, so we get delays when we have multiple concurrent resources and we've got entities competing for those resources. And so we've given a bunch of examples of those. So hopefully this is becoming kind of clear. But are there questions about this, you know, activities versus delays? Hopefully, since some of you have now done the hand simulations, you're starting to get a feel for how you can accumulate these wait times and how they're unanticipated without running the sim. But in case there are any other questions, does anyone have any other questions about any of this stuff? All right, again, I'm going to skip through some of this stuff since we took a lot of time on the lab. But you know, some of you, most of you have done the hand simulations, so you're familiar with this already. But there is a generic simulation execution for any one of these discrete event system simulations where you set the clock to the time of next event, and then at that event, You look at what is going on in that event, and that's going to set up certain logic, like somebody's service just ended, so do these things. Somebody's service is just beginning, do these other things, and so on and so forth. You do all those things, and that each one of those things might require you to schedule new events. Whenever you start a new activity, you also must schedule an event. Starting an activity means scheduling the end of that activity, because you know the activity's duration. That's the whole point of an activity. You know it ahead of time. Because you know it ahead of time, the instant it starts, you go into your magic 8-ball, you shake the magic 8-ball, you ask it, how long is this activity going to take? The 8-ball comes out and says it's going to take 8 minutes. So then you schedule the end 8 minutes later. And then you'll handle that later when the sim gets to it. And then you finally stop when you hit that end event, and that end event may have activities left over after it, and that's okay. You just leave them on the future event list. All right. So let's just skip through all of this stuff. This is just all the same slides from before, just kind of walking through that hand simulation. If there's any questions on how to build up this table as it flashes in front of you, and you can feel free to, we can chat about that. The big thing I want to get at here is that coming out of this chapter, I want you to feel comfortable with these terms, system and model. So we talked about a system, a collection of entities that interact over time. A model is our representation of that system. In our case, it's going to be computer simulation models, discrete event system simulation models primarily, but in general, models could be anything. They could be fashion models, they could be mouse models, they could be graphical models, and so on. Inside our discrete event system simulation models, because they're dynamical models, they have state. So they have things that change over time. And so the things that are changing over time, that represents the state of the system. Those system state doesn't change unless you've hit an event. So events are the instantaneous times where things change in the system. And the clock is a special state variable where it is representing the current time of the system. But we can view it as a state variable where it is also changing at the events. We have entities, which are kind of the things that we're watching going through the system, and each of those entities have attributes that differentiate themselves. We can create special state variables like lists, like the checkout lines, that'll help us manage the state of the system in a more convenient way. And then we have special lists that are not state variables, like the future event list. These are things that the simulation software use. We will reference periodically if we want to debug what's going on in our system. If things look funny, we might want to look at the event calendar or the future event list that the software is using and say, are things really being scheduled in with the right the distributions? And you might reveal then that, aha, I used the wrong unit somewhere because things that are supposed to be lasting an hour are lasting a minute. And so that's sometimes it's helpful to look at the future event list. But your simulation logic does not get access to the future event list. You can imagine that it's just totally hidden. It's like behind the fourth wall or something like that. It's just not available to your simulation, but it is available to you as a programmer for debugging reasons, but that's all. And then activity versus delay, which we've already talked a lot about. So that's the vocab for this chapter. So do you have any questions about that? Before, with the last couple minutes here, we'll talk about how to do the bonus on the spreadsheet if for those of you having trouble with that, for those interested in doing the bonus on the first homework. Okay. All right. All right, so on the homework, the bonus question says, do everything you did above, but do it in a spreadsheet. And I don't mean do it in a spreadsheet just like create your table in a spreadsheet. I mean, make a spreadsheet like they did in chapter 2 of the book, actually do the work for you. So can you implement a discrete event system simulation using a spreadsheet? And so then we have to ask ourselves, well, what is a spreadsheet and what are the potential challenges to implementing a discrete event system, a dynamical system in a spreadsheet? Well, we think about programming languages. There are 3 types of programming languages, main groups of programming languages. There's the procedural programming languages, which a lot of you might be familiar with. C falls into this group. Older languages like Fortran, Pascal, BASIC. These are things that where you've got routines where it says, you know, set X equal to this, add X to Y. do this, do that. Is this currently this? If it is, do this. If otherwise, do that. They're recipes. They're lists of instructions executed one by one. These are imperative. Each statement changes the state of a program. So that's the first group that we have. And then you have object-oriented programming. So now when you take earlier programming classes, now typically this is how we introduce people to programming, through object-oriented programming. In this case, data structures carry methods with them. And so rather than talking about everything in terms of a recipe, you sort of talk about the objects that are involved in the thing, and then you ask them to communicate each other with methods. And so you might have a way to turn on and off a light in a room. Well, then you have to access that via a switch. And so you have to ask the room to turn on its light. And so the room is an object, and it has a method which turns on the light in the room, and then that changes the state inside the room, but you don't have access to that state in the room. You ask the room to change its internal state. So they're hiding away all these state variables, and you're accessing them through methods. And so your job as a programmer is to write the methods, and other programmers will use your methods. And so that's kind of, it was a major shift away from imperative programming, was object-oriented, but it's somehow not that great of a shift. Spreadsheets fit within a different type of programming called functional programming. And this is a major shift in the way we think about programs. Here, a program output is simply a mathematical function of its input. This is a so-called declarative programming languages. Programming is done by employing expressions of relationships. There are no system states. There's no side effects because we don't see the steps. In a declarative programming language, you just say that A is related, A is an input and maybe C is an output. Then you say A is related to B by a particular relationship. B is related to C by a particular relationship. And then you just set up some input for A, and magically the output comes out for C. Behind the scenes, the computer might be executing steps, but you don't see that. The programming is done just by writing the relationships. That's a so-called declarative programming language. And that's where spreadsheets fall into play. You know that, when you write a bunch of formulas in a spreadsheet, sometimes it takes a while for the spreadsheet to calculate those formulas if it's a big spreadsheet. So behind the scenes, stuff's happening. But when you program that spreadsheet, you're just writing the relationship between one cell and another cell. You know that one cell is twice another cell. Another cell is the square root of another cell. Another cell is the summation of a bunch of other cells, and so on and so forth. You don't care how the calculations are done, but you want to trust that when you look at that spreadsheet, the numbers that are shown to you are going to be true with respect to the relationships that have been programmed into the spreadsheet. And this is a so-called cell-oriented data flow programming. Now, the big problem that we have with DES is that DES is built all upon state, but there's no state in the spreadsheet. And so it looks like we're not going to get through a lot of more of this today here. So I'll get through a little bit here just to kind of lay down roughly how things are done in the spreadsheet, but then you're welcome to continue to look at this. And I've actually got a link to last year's lecture on this as well, if you're wanting to do the bonus and need a little extra help. So the basic idea here is, and so this is an example I took from chapter 2 of banks, is that we want to then load into our spreadsheet. Each line of the spreadsheet is going to show the customers. And each customer is going to have that customer's inter-arrival duration and service duration. And we want the spreadsheet to fill out when each customer arrived, when each customer's service began, how long each customer spent in the queue, et cetera, et cetera. So rather than capturing the state of what happens at each time, now what the spreadsheet's going to capture is the relationship between each customers with each other, and each customer's with the state of the system. So now, instead of watching the state of the system unroll, I'm effectively just asking how do each customer relate to each other customer, and how does that tell me how long each customer had to wait? So as an example of that, if I wanted to populate down the arrival times, well, I know that for every customer, what will always be true is that the arrival time for that customer is the previous arrival time for the previous customer, that's the previous CRNs, plus the inter-arrival time for the current customer. if I write a spreadsheet formula that captures that relationship and I put it into this, this column, arrival time, and then I fill that column down, then because all of the inter-arrival times are known, I now know all of the arrival times for all of the customers immediately, like that. I don't have to go one by one. They're all known instantaneously as far as we're concerned with respect to the spreadsheet. So that's an easy one. So now I have to think, what other relationships do I know that help me forward simulate this discrete event system simulation model? And the other relationship I know, and this is a little more complicated one, is that every person's service begins either when they arrive, because they might arrive at an idle server, or when the previous customer's service time ends, the maximum of the two. So if you arrive before the previous service time ends, then this is going to say it's going to be just the previous service time. And oh, and there's a question for the homework's extra credit. Are we required to use a previous function? Now this previous is my pseudocode. So you have to use kind of, I'm trying to make it here to make it more clear what's going on. But when you actually write this yourself, you'll just write it in the spreadsheet using, you know, the basics of Excel or Google Sheets that you hopefully already know from previous classes. And so you're going to have a bunch of like equals B1, equals $B, $5, you know, et cetera, et cetera. And so that's what you'll put in instead of this pseudocode. So in these cells that you'll implement there, what you're going to do is implement a maximum between these two, and then that captures the relationship that every customer's service begins the later of the two, either when that customer arrives or when the previous customer's service time ends. And then if we do that, we can fill this thing down, and immediately nothing's going to happen because we don't know when the last person's service time ends is. But eventually, once we fill out this whole matrix here, then the rest of this will get filled down, but the relationship here is going to be true. For the homework, there's a question in the private question. If I submitted my table on Excel, no need to submit it in Word, correct? The grader is going to look for everything in the one document you submitted. We want you to submit any auxiliary stuff for you to be able to, for us, if we need to check anything, if we need to sort of make sense of some discrepancies, but we need it to be readable as a document that you can put in one document that the grader could just read down through that one document. So they don't have to click all through a bunch of different types of files, some which preview very well inside Canvas and some which do not. So if you've already uploaded your homework assignment and you've put your bonus in the Excel, then I'm asking you, if you can, to resubmit where you take that table and put it into your Word document with the rest of yours to simplify the process of grading. So you just have one document that the grader can grade. That's going to be a lot easier. It's still nice if you upload your Excel spreadsheet for other reasons that we kind of need both, at least for academic integrity and other sorts of things. But the grader is going to be grading what's in that Word document. Okay. So then the next step from this is to say, well, how much time do they wait in the queue? You have to ask yourself, what relationship's always true? The waiting time in queue is always the difference between when you arrive and when your service begins. So you write a formula for that. And we could go on through this. Every cell is just representing a relationship between that customer and the things that happen with other customers. And usually it's just going to be the previous customer. And so if we fill out all those things, then eventually, once we put in every last formula, everything will just magically fill out, and we'll have the whole discrete event system simulation model. And you should be able to look at the hand simulation you did in the earlier part of your homework and check it with the simulation that the Excel spreadsheet did. As an example, here it says that customer 3 left at time 13. That's what you did in the hand simulation. For this particular example. In yours, the numbers will be different. So then I can go down here and say customer 3, they left at time 13. So certainly enough, those things match up. And I could keep doing that. So there are a bunch of these other things that I can look at in this table up here and confirm in the table down here. And so the outputs are very, very variable. And so we're going to, again, have to use statistics as we talked about with the lab. All right, that wraps things up here. There was there was a question about, again, which so just to confirm, you want us to upload both an Excel file and add the Excel file to the Word doc. That's the preference. I need to see both documents for academic integrity reasons, but the grader is planning on only grading the Word document or the document you upload. So take an image of your spreadsheet, your output, and put that into the main document. And then if they need to check your formulas, then they've got the Excel to do that. But at least on the first pass, the grader is just going to be looking through the document. So your homework should be self-contained in one document. And that goes for everything throughout the semester, is that your submissions should be self-contained in one document. We might ask you to upload auxiliary documents that we end up using in different ways, but the one document the grader should, in theory, be able to do your grading just through that one document. You don't have to put the formulas in the Word document, but the output from the spreadsheet. Then if they need the formulas, they can then go look at the Excel spreadsheet you also uploaded. All right, so we've reached the end here. Let me give the attendance question, and then if there are any questions, I'm happy to take them after. But the last attendance question for today, so there was one earlier as well. So there's the link here. And so this question is, name one of the requirements necessary for a t-test, to use a standard, good old-fashioned two-sample t-test. What's one of the requirements you need? There's a couple of different assumptions. Just list an assumption as this question for the attendance exercise. So I'll put that in the chat. Needed to use a t-test. Good old-fashioned two-sample t-test. And with that, that's all I've got for you today. So you can feel free to pop off. I can also hang around for a couple of minutes if there's any other questions.
I have a quick question about, so I submitted my my lab last night, but I still got a message on Canvas later that evening that I had not submitted it yet, but should I not worry about that if I can see that my lab is submitted on time?
Yeah, if yours was submitted, so that message was sent by me. It's possible that you and I just happen to be both on Canvas at the same time. And when I said send to students who haven't submitted yet, you happen to be submitting as I was typing the email and hit go. And so it already cached the list of names. So it's possible that our just kind of missed each other in the night. So that, so as long as it looks like it's uploaded, you shouldn't have anything to worry about. And I apologize for the confusion.
Okay, thank you.
Any other questions? All right. So in that case, again, I don't really have anything else for you. So I am going to end the meeting. And if anything else comes up, feel free to send a note.